morning, ladies and gentlemen. Let's begin. How did the Hacksaw Blade Lab illustrate inertial mass?
What's inertial mass?
Inertial mass. Didn't we just talk about that? Okay, we're going to come back to this. This is the goal of today's lesson. Inertia is a property of matter.
Bill Nye, the science guy.
Bill Nye, the science guy. Cut to Bill.
Bill Nye, the science guy.
Science rules.
Bill Nye, the science guy.
Inertia is a property of matter. T minus 7 seconds.
So inertia is an object's resistance to change in its motion. More mass is more inertia. Mass is how much stuff is in something. So let's talk about our soccer ball and a bowling ball. If I was to kick this, well, you could do that. It wouldn't hurt too bad. But could I do the same thing with this? Would you want to? You might break your foot, right?
That's right.
You know, why is that? Well, more mass, more inertia, more resistance to change. Newton's first law of motion. An object in motion at constant velocity in a straight line path will stay in motion unless acted on by an outside force.
And
Part 2. An object at rest will remain at rest unless acted on by an outside force. Huh.
how can we show that?
This is an accelerometer, ladies and gentlemen. So we have the water, and we've got the bubble. And what I'm gonna do is I'm gonna accelerate it in one direction. Actually, let me stay where I'm at.
Whoa.
And the bubble points in the direction of the acceleration. Do you
Where's
see
the
it?
bubble, Miss Moore?
Bubble? Water.
Oh.
The bubble points in the direction of the acceleration. So bubble top. Whoa.
Why does the bubble go forward when you go that way, Miss Moore?
Well, what we're really actually looking at here is the water, which is pretty dirty, actually. Don't look too close. Okay. So what we're really talking about right now is the water. And the water has more mass than the bubble, than the air. And so what happens is as we move the accelerometer in one direction, because the water has more mass, it has more inertia, which means it doesn't want to move. It wants to keep doing what it's doing, which is chilling.
Yeah.
So as I move it, it wants to stay there. But then notice how once it gets moving, what it does. Comes back to the front.
Do that again. Whoa, it sloshes up.
It sloshes up. So as we're moving forward, it stays back, but when we stop, it moves to the forward. Why is that? Well, it's in motion, so it wants to keep staying in motion, so it wants to keep moving forward, but we've stopped, so it sloshes up. Right? So accelerometer.
Cool.
Get used to it. Force. A push or pull on an object. Force is a vector quantity. The units of force are newtons and represented by the letter N. Standing a little close there. I'm putting my force on the...
Too much force on the board.
Too much force on the board, okay. Force is required to overcome inertia.
Yeah.
Bubble cart. Where is that thing? Oh yeah. Force is required to overcome inertia. Should I go over here?
Yeah. What do we have here?
So this is our bubble cart, and we have cart, and we have bubble, and in the bubble is inside like a water, with water around it.
Yeah.
Okay.
Can't have bubbles without water.
Oh my gosh. Okay, so what I'm gonna do is I'm going to push the cart forward.
Okay.
Watch what happens to the bubble.
Oh.
Another one.
Okay, now we're gonna go in the opposite direction. Go.
Whoa. A little too hard. One more time.
One more time. Oh, when you pushed on it, the bubble went in the direction you were pushing. As soon as your finger came off, the bubble went back,
Let me try one more time.
and then
Push, back, and then. Oh, that was perfect.
oh, cool. Okay,
Force is required to overcome inertia. So there's 3 phases to what we just did. Now I know there's 4 numbers up here, but the first 2 are the same.
oh,
Okay.
okay,
So the motionless phase, we're just chilling there.
yeah,
Car's just hanging out. And then when I'm pushing it,
yeah,
and then when it's coasting.
yes.
And then it comes back to the first one, being motionless, stopped.
What was the bubble doing when it was motionless?
When it was motionless, it was just chilling in the middle.
Okay, and then
Right.
while you pushed it, what'd the bubble do?
When I pushed it forward, the bubble went forward.
Oh yeah, oh yeah,
Okay, and then while I was coasting, what happened to it?
it went backwards. That's kind of like this thing right here, yeah?
The bubble, right? So as it goes forward, remember the cart, we pushed it forward, the bubble went forward. We push it forward, the bubble's forward. We push it forward, the bubble's forward.
Yeah.
And then while it was coasting, it goes backward. The bubble, right? So coasting, oh, back.
When it's coasting, what's happening to the motion while it's coasting?
It's slowing down,
Oh yeah.
okay?
Is that an acceleration?
It is an acceleration. A negative acceleration. Right, the bubble points the direction.
What kind of acceleration?
Negative acceleration.
Okay.
And don't forget, the bubble points in the direction of the acceleration, so it's negative. It makes sense that it's in the back, right?
It does, yeah.
Okay, I've talked enough about this. Shall we draw our stuffs? Okay, hold on, I gotta erase this. I forgot to erase it. Free body diagram are useful tools. Oh, I need that for later. Come back here. Free body diagrams. These are useful tools for visualizing the forces being exerted on a single object and writing the equations that represent a physical situation. Okay, make sure you've got that written down, but here's what you need to know. A free body diagram means that you don't have to draw the cart. We are just going to use a dot to represent the cart. I'm going to go ahead and draw some free body diagrams to represent our cart on the table as it was stopped, as we pushed it.
Yeah,
pushed,
while you're pushing.
and then while it was in motion, coasting. Okay. So again, for free body diagrams, we do not have to draw out the cart.
So boys and girls, do these in your notes while Ms. Moore shows you.
Do these in your notes now, please. Thanks. Okay. All right, so we've got our dot to represent the cart. Now what? Well, my first question for you guys is, what forces are acting on the cart?
Well, force of gravity is pulling down.
Okay, force of gravity, pulling down. Now the force of gravity should be the same for all 3 of these, right?
Yep. Same weight cart. Yep.
Should be the same.
Is good.
Okay. What else? If I put this bowling ball on the table, what's keeping it from falling?
The table.
The table, right? So that must mean that the table is pushing up or exerting a force up on the bowling ball, while the bowling ball is also being experiencing the force of gravity being pulled down. So how can we represent this? Well, right now we're going to call it the force up. And again, it should be the same. And these should be the same.
Yeah.
Like, not drawn to scale.
They cancel each other out.
Yeah, and you can see that right here, right?
Yeah.
So as it stopped, it's just hanging out there. Should I go grab the cart? So So when it's just chilling here, are there any other forces acting on it?
Nope.
No. Okay, so we're done here. Let's go ahead and take a look at when it's being pushed.
You pushed it.
I pushed it. I pushed it.
That's a force.
That's a force. So I'm going to go ahead and draw the force. I'm going to call it the force of push.
I like that.
Okay. Now, why does it coast? Well, we asked this question earlier. When it's coasting, what is it doing? It's slowing down, right?
What's causing it to slow down?
What is causing it to slow down? Not the accelerometer.
Its inertia makes it want to keep going.
Yeah. So what's going on here? Well, what color shall I use? We'll
Red.
use red. Red.
Red.
Okay. So we have what's called the force of friction, and we're gonna draw it. A little too long there. We're gonna draw it this way. I'm gonna call it force of F, force of friction. Okay. So the next thing I want to do is I want to talk about net force. So we need to take a look at all the forces and add them up in each step.
What does net mean?
Net? Net means when you add up everything that there is there.
It's kind of like the total.
Yeah, the total. There we go.
I like
I'm like basketball and net. Okay.
There you go.
Wrong. Okay, so
Swish.
when we look at this force and we add them up, they cancel out, right?
Yeah.
So our force net here is just 0, right? They cancel.
Yep.
Over here, same thing. These guys cancel, but what about this guy?
That's the only one left.
Yeah, so I'm gonna go ahead and draw it that way, okay? And then again, these cancel right here, but what about this guy?
That's the only one left.
That's the only one left, okay. All right, so we've got our net forces. Let's talk about the bubble. Where was the bubble at each step? Well, when it was stopped, it was just in the middle. Wow, this is a good looking card right
It
here.
is. It's just right there.
In the middle.
So the bubble's in the middle and it's just sitting there.
Okay. Now when we pushed it forward,
Whoa.
oh, it goes, what did I say? Forward?
Yeah.
Up, forward, bubble, oh, I got you. I went like this. Bubble forward, right?
Yes.
And then when it's coasting, okay, we push it forward, and it's coasting, it starts to head back.
Goes backwards.
Okay, so bubble back.
Not very good camera work here. Sorry, boys and girls.
I blame Mr. Bookett. Okay, so the next thing we want to look at is the acceleration.
Well, the bubble's like an accelerometer, isn't it?
The bubble tells you which way it points towards the acceleration. So all we have to do is look at the bubble here. Do we have the bubble pointing in a direction here?
No.
No. So acceleration equals 0. Huh. Net force 0, acceleration 0. Okay.
Oh.
All right, okay, come over here. So bubble is going this way, so our acceleration is also going that way. Okay, here our acceleration is going, our bubble is going this way, so that means our acceleration is going that way.
Oh.
Okay, all right, something going on there. All right, sweet. So I think that concludes our fruit body diagram, yes?
I think so.
An object at rest will remain at rest unless acted on by an outside force. So let's talk about the water.
It's just chilling.
It's just chilling, right?
Yeah.
And then when I put the force on it, when I move it this direction, it wants to stay at rest, right? It sloshes up against the back.
Oh, yeah, I get that.
All right, let's go ahead and go to my next one here. You've seen this before. An object in motion at constant velocity in a straight line path will stay in motion unless acted on by an outside
So
force.
you get it moving.
So we get it moving and the water wants to keep going,
Whoa.
but then it sloshes up against the front. It's stopped. It's acted on by an outside force.
Ah, that makes sense. And it's the same thing going on in here, yes?
Mm-hmm.
All right.
Same thing, same thing. When forces are balanced, no acceleration occurs. Equilibrium. Okay. Forces are balanced, no acceleration. Over here, they're not balanced. We have an acceleration.
Yeah.
Over here, they're not balanced. We have an acceleration. Okay, so Newton's 3 laws of motion. We just talked about the first one, but overall, they show the connections between the properties of an object and what it takes to move it. All coming back to that inertial mass. Newton's second law shows the relationship between how massive an object is, the size and direction of the net force acting on it, and the resulting motion. Blah, blah, blah. Okay. Oh, not yet, Belle. Not yet, Miss Moore. Okay. So we have a few. Shall I start with this one?
I would.
Yeah. Okay, so we have a ping pong ball here. And what I'm going to do is I'm going to pull this back slightly and let it hit the ping pong. Pay attention to what happens. I'm going to use a certain force.
That was weak.
So that
Come here, you.
what should I do this time?
Whip that sucker.
Let's put more force on it. Wait, I messed up a little bit.
Whoa! That went much farther.
Should I do the next slide real quick and talk about it or not yet?
Well, what if you used a golf ball?
Oh, what if I used a golf ball? Okay. So first of all, what's the difference between the golf ball and the ping pong ball? More mass. Okay, but again, I'm gonna go ahead and add just a little bit of force.
Ah, weak, weak.
Still weak.
Caught it. All right.
Okay, pleasure on there.
So
Okay.
that's Newton's second law.
Can I put more force?
Hit it hard.
It looked a little bit faster though, yeah?
Yeah.
Okay. All right, so
Huh?
here's what we need to know. The more force that we hit, so think about that first one, the ping pong ball. The more force we hit the ping pong ball with, the further it went, right?
The greater the acceleration.
The greater the acceleration. Oh, sorry. The more force that we hit the ping pong ball with, the greater the acceleration, the further it flew.
Yeah.
Now think about the ping pong ball compared to the golf ball. Well, which one had more mass?
The golf ball.
The golf ball. So the golf ball did not go as far because it had more mass. It has more inertia, which means it doesn't want to move. Right? It wants to keep doing what it's doing.
So you got to hit it like with a golf club.
Okay, so I'm actually going golfing this weekend. I've literally never been. It'll be interesting. Okay, another way to write this. Force net total equals m times a. And these are your units. So when we talk about force, we're talking about newtons. And how do we get this newton? What does this actually mean? Well, it just means a kilogram meter per second squared. Because these are the units for acceleration, and that's the units for mass. Where force and acceleration are vectors, and the direction of the net force is always the same as the direction of the acceleration.
We saw that.
Okay, so acceleration, net force, same direction. Acceleration, net force, same direction. Oh, no, they're there. Okay.
Well, zero is the same direction as zero.
Yeah, I guess so. Friction. Oh yeah, that word, F of F. A force that always opposes motion. Now, remember we pushed it this way, it's moving this way, so the force of friction has to be that way.
It's opposing the motion, that's right.
Okay. And, well, this pretty much covers our free body diagram talk. What I want you guys to think about, well, let me talk about this real quick. Just to review, dot represents the center of the mass of the object, so our dot over there for our cart. The arrows are drawn to represent the magnitude and direction of all the forces acting on it. And the net force is found with vector addition. Ooh, vector addition.
Oh, we were adding vectors over here?
Okay. My last question. What would be an appropriate system for the bubble cart?
Huh.
If we're thinking about the bubble cart, we have to think about all the forces that were acting on it. Obviously, the bubble cart is involved.
Yes.
And what is holding the bubble cart up from falling?
The table.
The table, right? So bubble cart and table, but we know that the force of gravity is involved, and what's involved with that?
The Earth.
The Earth. So our whole entire our system. Remember, we talked about systems and how important they are. The world is a complex place. Let's simplify it within our system. Our system is our cart, our table, and God's good green earth. All right, and here's your homework. I'll put this on the next page for you. Quizlet number 2A. They just more and more Quizlets. And yeah, we should be able to do this. Show all your work.